Okay, let's continue. Here is another concept, limit points. Okay, let A be a subset of a space X. A point X in X is called a limit point. This is also called cluster point. Or accumulation point of A if the following happens: if every neighborhood U of X contains a point in A from A different than X. So what's the limit point? It is the following: whenever you take a neighborhood, in other words, an open set in X, in this open set, there should be some element of the set A, okay? There should be some element here, let's say Y, and this Y should belong to A. If this is the case, for every neighborhood of X, then we say that X is a limit point of A. Equivalently, this means the following. By the characterization we proved earlier, equivalently, a point X in X is a limit point of A if and only if X belongs to the closure of A minus X. Right? Recall that we characterized points in the closure of a set. So a point belongs to the closure of A minus X if and only if every neighborhood of that point contains some elements from this set. But this means that every open set containing X contains a point from A that is not equal to X. Okay. Therefore, this is an equivalent formulation of a limit point. Okay. So here's a characterization. Maybe before this characterization, okay. Şöyle diyeyim. Okay, let A be a subset or subspace is of a space X. Let A prime be the set of all limit points of A. Then we have this. A closure is equal to A union limit points of A. Okay, so this is also a characterization of closure, right? Closure contains A and the limit points of A. And proof is again easy. Actually, we just said about it. Every limit point of okay, note that every limit point of point X is in the closure closure of A minus X, right? Şurada yaptık onu. Bir tane point, so a point in X is a limit point of A if and only if X belongs to the closure of this set. So if X is a limit point of A, then X is in the closure of this set. But you know, A minus X is a subset of A, right? A minus X is a subset of A. Therefore, it's a subset of closure. And now this is a closed set containing this set. Therefore, this closed set contains also the closure of this set. So what we see is then any element which is in the A prime, in other words, it's a limit point of A, then that element belongs to A closure. Hence, A prime is contained in A closure. Clearly, A is in A closure, and thus A union A prime is inside A closure. Okay. Peki şimdi ne yapmamız lazım? Now we have to prove that A closure belongs to A union A prime. Okay, now for the converse or reverse inclusion, let X is in A closure. I have to show that X belongs to this. Well, assume that X is not in A. Okay. Yani I want to show that this point is inside this union. Suppose that it is not in A. Now I have to show that X belongs to A prime. So in other words, it must be a limit point. of A. Okay. Now, since X is in the closure, every open set containing X contains some elements from A. But that element cannot be X because X is not in A. Okay. And what was the definition of being a limit point? Limit point means that every neighborhood of X contains a point from A which is different than X itself. So let U be a neighborhood of X. Okay. Since X is in A closure, U intersection A cannot be empty. However, X is not in A by the assumption, and thus U intersection X, which is not empty, contains a point different than X. But that is exactly the definition of a limit point, right? So here, okay, I took a neighborhood of X, and then we showed that U minus A contains a point different than X. So this means, hence, X is the limit point of A. And we are done, right? So X is in A prime, which is in A union A prime. Therefore, A closure is inside A union A closure, and hence zaten diğer tarafı göstermiştik. A closure is equal to A union A prime. Okay. Okay. A corollary of this, a subset of a topological space is closed if and only if it contains all of its limit points. Right? This is just a trivial consequence of this theorem. Why is that? So if A is closed, then A is equal to its closure, but then this means that limit points belongs to A. If A contains its limit points, then of course this union is equal to A, but this means A is equal to A closure, therefore A must be closed. So these two statements are equivalent. A subset is closed and that subset contains all of its limit points. Actually, that's also one reason why we call such a set closed, because it contains all of its limit points and ends of that, it contains its ends somehow. One way of imagining uh, uh, closure or limit points is that you may consider those limit points as its ends, kind of. Therefore, if it contains all of its ends, then we may, we say that it is closed. Okay. Sorusu olan var mı arkadaşlar? Hı. Aha. O daha önce yok, şurada onu ispat ettik de ondan. Ee, şöyle. Bir nokta closure'da demek o noktayı içeren her open set'in A ile kesişmesi demek. Bunu kullandım. Şu teoremin A şıkkını. Tamam mı? Yok, sorun değil. Yani hepsi basit basit ama bir sürü şey var. O yüzden işte bir yerden sonra birbirlerine girmeye başlıyorlar. İşte siz bu şeylerle, exercise'larla, sorularla uğraşarak bu konseptleri böyle oturtmanız lazım. Hani basit basit nesneler ama bir sürü olunca karışıyor. Yani orası kesin. Yani benim de kafam karışıyor bazen. Ne neydi? Ya önce hangisini tanımlamıştık vesaire. Yani dikkatli olmak lazım. Başka soru soran var mı? Okay. Another topic is called so-called Hausdorff spaces. So far, all the spaces we have studied were Hausdorff. So you may think this. You may think that this definition is kind of useless because uh, every space was like this, right? But we will see later that not every space is actually Hausdorff. So far, we studied mostly metric spaces, and metric spaces are always Hausdorff. But there are non-Hausdorff spaces. So let me define what's Hausdorff. Okay, a space, I mean a topological space, of course. A space X is called Hausdorff. Hausdorff. For every distinct this for every uh, pair of okay of distinct points x1 and x2. So whenever I take 2 points which are different from each other, then there are okay, and there are disjoint open subsets U1 and U2, so that X is in U1 and X1 is in U1, X2 is in U2. So a space is called Hausdorff if you can separate points by open subsets. What we mean is this. Whenever I give you 2 points, okay, you can always find open sets U1 and U2, and the intersection of these open sets is empty. If you can do this, then that space is called Hausdorff. Of course, every metric space is Hausdorff. Rn with standard topology, Rn standard is Hausdorff, right? Also, every metric space is Hausdorff because whenever you are given 2 points in Rn, you measure the distance between these 2 points. It's a positive number if the points are different. And then you draw balls with radius, let's say d over 3. Okay, so this radius is d over 3 and this radius is d over 3. Then these 2 balls are open and they are disjoint. So Rn with its standard topology is Hausdorff. Okay. Sorusu olan var mı? Okay. Şöyle bir örnek yapalım. Non-Hausdorff space. Mesela şöyle olsun. So X has just 2 points, A and B, and tau has 3 open sets. Empty set, the set containing A itself, and the whole space AB. Okay. Well, this is not Hausdorff. Why is that? Note that A and B are different points, but you cannot find 2 open sets containing A and B which are disjoint, because any open set containing B, well, actually there is only one open set containing B. It is the whole space, and of course that contains also A. The only open set containing B is X itself. Hence, this space is not Hausdorff. Okay. Actually, there is more. Okay, every finite point set in a Hausdorff space is closed. So if I take a subset of a Hausdorff space, and if that space contains only finitely many points, then that subset must be necessarily closed. Why is that? Well, it is because of the following. Okay. Every actually singleton is closed. Why is that? Okay. For any x in X, the subset x minus little x is open. Neden open bu? Şu yüzden this is because if y is in y minus x, then y is different than x, and thus there are open subsets u v of x with what? X u'nun içinde, y v'nin içinde ve u'la v kesişmiyorlar. Ama o zaman ne elde etmiş olduk? In particular y is in v and u and v are disjoint and x is in u, therefore this is in x minus u, no, x minus little x. So we have obtained what? For any point in this subset, right, I find an open set V containing Y, and that open set is contained in this subset. This means that x minus little x is open because every point of x minus little x contains an open set containing that point which lies inside x minus x. So since this is open, the singleton is closed. So this set is closed. Okay, closed in x, right? Because its complement is open, therefore this is closed. But if this is closed, then we know that finite union of closed sets is closed. Finally, if A, let's say x1 up to xn, is a finite set, then what is A? Well, A is just union of x1, sorry, union of x2 and up to xn, which are all closed sets, therefore their union is closed, which is closed. Because it is a finite union of closed subsets. Okay. Bir tane daha benzer bir şey var, tanım var. Onu da söyleyeyim. Bu Hausdorff olmaya benziyor. Definition diyeyim. A space X is set to satisfy the T1 axiom if the following happens: if for any two distinct points x1 and x2 of x, there is an open set. With the following. Bu open set U'yu içerecek ama pardon x1 open set'in içine kalacak ama x2 kalmayacak. Bunu yapabiliyorsanız o uzaya T1 uzayı deniyor. Right? So a space with this property is called a T1 space. So let me explain what this is. So here's I have 2 points. Whenever I have 2 distinct points, I can find an open set containing x1, I mean the one I choose, that contains x1 and that doesn't contain x2. Of course, if x is t1, then there should be some open set containing x2 and not containing x1. So there must be also some open set like this, which contains x2 and doesn't contain x1. However, sometimes it is not possible to choose this u and v so that they are disjoint. Okay, so a space can be T1 but may not be a Hausdorff space. Okay. Örnek de vereyim. Okay, yeah. Örnek o kadar kolay değil ama okay, onu şimdi veremem. Evet. Neyse, tamam. Okay, a space şöyle diyeyim. Note that every Hausdorff space X is T1. Okay, T1 means it satisfies the T1 axiom. We will see later that there are non-Hausdorff T1 spaces. Okay, and let me give its name. One example is, for example, the real line with double origin. Okay, we will study this when we consider quotient spaces. There I will mention this example. Okay. Okay. Now there is one result about limit points and these axioms. Let X be a space satisfying T1 axiom. So it's a T1 space. Let A be a subset of X. Okay. And the point then a point X is the limit point of A if and only if every neighborhood of X contains infinitely many points of A. Therefore, if you are in a T1 space and if the space is a finite set, if it contains only finitely many points, then it has no limit points, right? Because this theorem tells us that if there's a limit point, then there must be infinitely many points in A. Okay. In other words, in a reasonable space, in a T1 space, to talk about limit points, first of all, your space should have infinitely many points. Okay. Proof is easy. Okay. So let X in X be a point, be a limit point of A. Well, this means that every open set containing X, every neighborhood of X, contains a point from X, from A, which is not uh, equal to X. Okay, so let U be a neighborhood of X. Ne göstermem lazım? Şunu göstermemiz lazım. Must show A intersection U is infinite. Okay. Şimdi şunu biliyoruz. Demin yukarıda a while ago I proved that every one point set in a Hausdorff space is closed. But actually the same proof works and every one point set in a T1 space is also closed. Okay. Şöyle diyeyim. Note that every one point and hence finite subset of a T1 space is closed. Right? Just as in the case of Hausdorff spaces, the same proof actually applies. You don't need the full strength of being Hausdorff. Just being T1 is enough for a one-point set to be closed. And if one-point sets are closed, then of course their finite unions, which are just finite subsets of the space, are all closed. Now, if A intersection U is finite, şöyle diyeyim. Now, if A intersection U is finite, then of course V, which is just U intersection X minus A intersection U. Yani şöyle yapsam yeterli yani. This is a open set in X. This is a closed set in X. I subtract this closed set from the open set. This is actually the same thing as this, right? Intersection of this open set with this open set. Therefore, V is also open. Is open and okay. Şöyle diyeyim. Pardon, şöyle. Okay. Şöyle diyeyim. Şu finite'den şu da finite bir set. Şimdi V ne demiştik? U'dan bunu çıkartacağım. Ama eğer X buradaysa X'i çıkartmak istemiyorum. Dolayısıyla X'in dışındakini çıkartayım. Yani I look at this intersection. It's a finite set, but it may contain X. I don't want to take out X from U because I want this to be still a neighborhood of X. So I just delete the points which are contained in this intersection other than X. Okay. Now this thing is an open set, is open. Why is that? Because this is open and this is a finite set which is closed, and I subtract a closed set from something that's intersection with an open set. Therefore, this is open in X. Moreover, clearly X is in V since X is in U, right? U is a neighborhood of X, therefore U contains X, and I make sure that I don't take X out, okay? So this is an open set containing X. But now However, what is the intersection of this with A? Well, this thing, this intersection, so I took out all the points in A which lie in U other than X. Therefore, this intersection can contain at most X. However, this thing, okay, is either empty or equals this thing. So this gadget has no points different than X. Therefore, so X cannot be a limit point of A. And this is a contradiction, which is a contradiction. Nereden çıktı bu contradiction? Why we ended up with this contradiction? We ended up with this contradiction because of the following assumption. I said, if A intersection U is finite. So hence, A intersection U must be infinite. The other direction is clear, of course. If every neighborhood of X contains infinitely many elements from A, then clearly that neighborhood contains a point different than X, right? Conversely, if every neighborhood of X contains infinitely many points from A, then it clearly contains points from A that are different from X. Değil mi? Sonsuz tane nokta varsa bunlardan birisi X olsa bile geri kalanı X değil. O yüzden de X'in dışında da noktalar içeriyor A kümesinden. Dolayısıyla ispat biter. This finishes the proof. Dolayısıyla ne ispat etmiş olduk? Şunu yaptık. Eğer bir uzay T1 ise so if a space is T1, then for a point to be a limit point of a set, first of all, that set must be an infinite set, and every neighborhood of X should contain infinitely many elements from that set. Okay? Okay. All right, let me stop here. Next time I'll start from this point and continue proving almost trivial statements. Statements are trivial mostly, but as they accumulate, things becomes non-trivial. All right, let me stop at this point.